Video. I don't know if you watched it or not, but we started on 14 and then I had to stop. So we'll just briefly go over what we were talking about before. We're trying to determine if the braking distance is proportional to the kinetic energy. What it means to be proportional is that it will be a straight line and pass to the origin. That's directly proportional. Then it could also be proportional to the square or something like that. But in general, if we're just seeing proportional like this, we should be seeing a straight line passing through the origin. So what we do is we graph these values and we graph these values. Like these are our x coordinates and these are our y coordinates, which I've done here. And then we can see I can draw a line passing through the origin, which is there. And this line goes very close to all of these points on there, right? So the answer here is, does the graph show that the student's suggestion was correct or incorrect? We'd say correct, right? Because we can draw a line that is close to all the points and passes at the origin, right? So that's, what I said you'd write there. Next one says, use your graph in the following equation to predict a braking distance for a speed of 35 meters per second. The mass of the car is 800 kilograms. Show clearly how you obtain your answer. So we have a speed of 35 meters per second. The mass of the car is 800 kilograms. So we're going to find our kinetic energy, which is going to be 1/2 times 800 times our velocity, which is 35 squared. All right, so we get out our calculator and we do this. Half of 800 is 400, so we can avoid that. 35 squared, I don't know, let's see. 35 squared is 1,225 times 400 is 490,000. So this car moving at 35 meters per second has 490,000 joules of energy. Which is 490 kilojoules, right? Because notice the graph up here is in kilojoules, right? So what we do is we go up here and we'd find 490 kilojoules. Again, this is kind of like a math problem. So 490 kilojoules is here, and we would look at, coming straight across, what is our, based on the trend line, what is our predicted braking distance? Come down here, right there, right? So it's 50, 60, 62, about 62 meters. And now that might vary a little bit if you drew this trend line slightly differently. Or you could go to technology, and I think I have it on here right here. So here's there's the best equation for it using technology. And then I could actually predict using this equation if I wrote f of x equals 7.85501. I'm getting that from here, right? The m value. That's that equation. And then I want to say if I plug in 62, do I get out 490? Pretty close, right? I could try 63. That's a little bit over, so 62.125. There you go, 62.5. 62.4 is probably even closer, but you can't get that just based on the graph, right? So that's that. Next, the diagram shows the car before and during a crash test. The car hits the walls at 14 meters per second, right? So the moment it hits, it's 14 meters per second, and it takes 0.25 seconds to stop. Calculate the deceleration of the car, right? How fast does it decelerate? So some things we might want to talk about are, well, the car had momentum before, and after the change in momentum, it doesn't say if it stopped completely, right? I'm assuming it does, right? It completely stops into that wall. But we could talk about impulse, which is the change in velocity. The impulse is the force times the time, which we have this time, and we have a velocity. We don't have a force, right? So that one doesn't quite help us. We also know that force equals mass times acceleration. This might help. So we might say, oh, impulse is mass times acceleration times time. And that's impulse is also equal to the change in momentum. P is momentum. So in this case, we have some things that we could plug in. The car is the same car as above, right? So a car, maybe it's not the same car. Hold on a second. Okay, now this one's more basic than it seems, right? So all we need to do is find the deceleration of the car, right? And so all we need to know is acceleration. What is acceleration? Acceleration is change in velocity over change in time, right? So acceleration is change in velocity over change in time. In this case, the change in velocity, it went from 14 meters per second to 0. So it decreased by 14 meters per second, and it took it 0.25 seconds to do that, right? So it's 14 divided by 0.25, which is the same thing as 14 times 4. So 56 meters per second squared is our acceleration. Right, and it's important on the test when you do this that you show some of your working, right? Show what you start with, show what you plug in, show what you get when you're done, right? In an accident, the crumple zone at the front of the car collapses progressively. This increases the time it takes for the car to stop. In a front-end collision, the injury to the car passengers should be reduced. Explain why. The answer has been started for you. By increasing the time it takes for the car to stop. So again, impulse is force times time. Right, and impulse is change in momentum equals force times time. So what we're saying is what we're saying is the force of an impact, right? Momentum is change in momentum is the how you feel the impact. If I increase the time, then I decrease the force because of this equation, right? So by increasing the time it takes the car to stop, the force decreases. And since it's force, right, it's the force that we feel. The force is the things that causes energy, right? Like how much force is exerted is how injured you get. Because we're decreasing the force, that leads to less injuries, right? All right, next one. A racing driver is in his car along a straight road, as shown in the diagram below. The driver pushes the accelerator pedal as far down as possible. The car does not accelerate above a certain maximum speed. Explain the reasons for this in terms of the forces acting on the car. He's going to accelerate and accelerate and accelerate and go faster and faster and faster, right? The accelerating means his velocity is increasing. Eventually he reaches a very fast velocity, we think. But some other things also increase. The wind resistance, right? The wind is pushing on this thing, and that frictional force of the wind, the air resistance, will slow the car down. And there will be a time at which that frictional force caused by the wind and the tires on there too, will be as great as the force that the acceleration of the engine can produce, right? So there's this point where it can't accelerate anymore because the force at which the engine exerts is equal to the force at which the wind and the tires, the friction from the tires is exerting. And so it becomes at an equilibrium, traveling at a constant speed once it reaches that. It's kind of like terminal velocity when you fall, right? You start falling and you go faster and faster and faster and faster and faster, right? And then eventually you reach a point where you can't go any faster because the wind resistance is pushing against you just as hard as gravity is pulling you down, right? And so eventually, if you jumped out of an airplane, you would reach what we call terminal velocity, which would be as fast as you can go as you go down. And the same thing happens with the car. It's just the wind resistance and the friction of the pedals or tires against the ground. Okay, now we're given some information. The car has this kind of mass. When the brake is pushed down, a constant braking force of 10,000 newtons is exerted on the car. Calculate the acceleration of the car. So what we know is force equals mass times acceleration. They give us the force, right? Newtons is force. They give us the mass. and they ask for the acceleration, right? So we just have to solve this, divide both sides by 1,250 kilograms. So 10,000 is 8 meters per second squared, right? And again, this is the work you're showing, and that's the answer that you're getting. All right, calculate the kinetic energy of the car when just traveling at a speed of 48. So just have to remember that kinetic energy is 1/2 mass times velocity squared. So that's 1/2 times the mass of the car is 1,250, and is traveling at 48 meters per second, and you have to square that. This one didn't show velocity squared. Again, that formula is given to you, so you don't have to worry about memorizing it. Although hopefully you have it memorized by now. It's not that difficult. And you should get the kinetic energy is 1,444,000 joules, right? This thing has a lot of energy, almost 1.5 million joules. So that goes there. When the brakes are applied with a constant force of 10,000 Newton, the car travels a distance of 144 meters before it stops. Calculate the work done in stopping the car. So remember, work is force times distance. Another way to think about work is change in kinetic energy. So I think we could actually solve this one a couple different ways. So in this case, force and distance, we could multiply 10,000 times 144, and this is newtons and this is meters, and you would get 1,440,000 Newton meters, which are the same as joules. Another way to do it is change the kinetic energy. This thing had this much kinetic energy, right? And then we changed the kinetic energy down to 0, right? Because it's stopping. Stopped things have 0 kinetic energy. And so the change in kinetic energy is the same as this one, right? Which is the same as that one. So that's another way to think about that. All right, so let me pause and get the rest of these problems up. Okay, 16, we're sliding a 20 kilogram object across a horizontal surface, which means we're going to start this one. We have a horizontal surface, and we're sliding an object across that surface. This object weighs 20 kilograms. The frictional force is 30 newtons, and the object is being pushed with 50 newtons. So there's no need to calculate static friction or kinetic friction because they just tell us what the amount of friction that's has on it already. Let's assume it's going this direction, which means our applied force is 50, right? There's also a frictional force pushing against it, which is 30. Notice how it's smaller because it's a smaller quantity, smaller magnitude. And then we also have the force of gravity, and we have a normal or support force, right? And those two should be equal because it's not sinking into the ground and it's also not floating off into the air. Next is how much work is done by the pusher on the object. So remember, work is force times displacement. In this case, the person is applying 50 newtons of force times 30 meters. And so this person is doing 1,500 Newton meters or joules of work. And you might say, hey, but remember when you said that work is force, displacement, and also cause? The force has to cause the displacement. And so this 50 did cause this displacement, but there's also this friction that's pushing against us. So not all of this work went towards displacement, right? Well, let's talk about that in a second, right? So how much work is done by friction? And this is kind of like negative work, right? So the work done by friction is 30 newtons, right? Because that's the friction times 30. meters, which is, so this is the work from applied, this is the work of friction, and you get 900 joules. And so if you thought about what's the total work done here, well, it would be the person actually did 1,500 work. Let's not say total, let's say net. That's a better word in physics. The net work here is the person did 1,500 joules of work, but then so did friction. Friction also did 900 joules of work in the opposite direction. So you could almost think of this as like negative energy. And so the net work is the 1,500 minus the 900 joules. And that's not answering this question, but you'll need that in a second. So the network is, it's funny, 600 joules. That's how much work actually gets done, actually gets seen. Everything else, all that other energy goes towards heat and thermal energy, right? Predict the speed of the object, including any assumptions you have made. So a really good way to think about, to get a speed here is to talk about kinetic energy. Remember how we said kinetic energy is, the change in kinetic energy is equal to the work, and really this should have been net work, right? And we have the net work here, so this is 600 joules. The change in kinetic energy is here's where we have to make an assumption, right? Let's assume that it started at 0, or you could say, oh, well, let's assume it starts at 5, whatever, but it's easier to say it starts at 0 meters per second. Let's say the block was at rest when we started. And then the change in kinetic energy is from 0 to however much, 0 to whatever speed it ends up being, right? So the change in kinetic energy is just going to be 1/2 mass times velocity squared, right? This would get more complicated if you said you started at 5, because then the change in kinetic energy would actually be this minus 5 squared. You have to find that you'd have to subtract 1/2 20 times 5 squared from your 1/2 20 v squared, right? And so it's easier if this number is just 0, because then this whole thing just goes away and you're just left with that, right? So the change in kinetic energy is just 1/2 times 20 velocity squared, because we're assuming it started at 0. And then we can just solve this, right? So this is 10. Divide both sides by 10, you get v squared equals 60. And you take the square root of both sides, and square root of 60 is about 7.75. And that's meters per second, right? Stating the assumptions. Remember, their assumptions was that the block started at rest, right? All right, maybe I'll make one last video for these explaining and analyzing